Okay, now we are going to look at another example of the Laplace transform of a power signal, like t to the n. And so far, we've looked at the Laplace transform of t. So let me just write it down here. So we looked at the Laplace transform of t, which we found to be 1 over s squared. And next, we are going to look at t to the n. Again, let's write down our Laplace equation. So we want the Laplace transform of t to the n, which is integrating between 0 to infinity, e to the minus st t to the n dt. So just like before, we are going to use integration by parts, and let u be, we can choose u to be t to the n because it will be easier to differentiate this, t to the n. So du is equal to n times t n minus 1 dt. Then we can choose our dv to be e to the minus st dt. Hence, the antiderivative of that will be minus 1 over s e to the minus st. So now we can use the integration by parts equation. Let me just write this in the different color. It's uv minus integral of dvu. And we can substitute our terms. We chose u to be tn. So we have t to the n times v, which is minus 1 over s e to the minus st, and minus integral between 0 to infinity. V, again, we have negative 1 over s e to the minus st. Let me just choose some brackets here so that I can separate this so that we know what we are doing. Times du. Du is n times t to the n minus 1 dt. Okay, that's what we have. Now we can evaluate this. We are going to evaluate it between 0 to infinity, and when we do that, let's just write it out first so that we can see where things are going and where things are coming from. Here I think I forgot a negative. Did we have a negative? Yes. No, it's fine. So I can pull out, if t goes to infinity, we are going to have a minus infinity to the n, okay, times 1 over s e to the minus infinity, okay, minus, then we are evaluating with using our lower part. It's 0 to the n times 1 over s e to the 0. Okay. So let me just look at this part first. The part that we are evaluating is only this part first. Okay. Let's look at that. Now, this part here, the infinity part, one will be thinking, okay, infinity times 1 over s e to the minus infinity. Infinity is a big number. Ain't that going to be infinity? And the answer is no. Reason is simple. This part, the e to the minus infinity, it will go to 0 faster before the t goes to infinity. You need to remember that. And since it's going to 0 very fast, it will drive this whole equation to 0. Hence, that's going to be 0. Now, the next part, we know e to the 0 is 1. However, we have 0 to the n. So, that's going to drive this to 0. Now, the only part that we have is, remember, is minus the integral. So, let me just rewrite this. I'm going to pull out the constants. So, n is a constant because we are integrating with respect to t, and your minus 1 over s is a constant. Minus and minus is going to be plus. So I'm going to rewrite this. Let me rewrite it in a different color. Which color can we choose? Let me choose this one. Okay, so plus integral between 0 to infinity. We said we were going to pull out the constants, so let me just do that. So we're gonna have n over s, integral between 0 to infinity. Now we have e to the minus st times t n minus 1 dt. So let me just create enough space to write. Now we can see that this, from the definition of the Laplace transform, we say that the Laplace transform of any function is equal to f of s, which is integrating between 0 to infinity. Take your function times e to the minus st dt. Now, from this equation, we can see that this part is our function, and this part is your e to the minus st. So we can just say that, look, this is just the Laplace transform. This part is the Laplace transform of our function t to the n minus 1. So now we have the Laplace transform of t to the n. It's equal to n over s times the Laplace transform of t to the n minus 1. Okay, now can we say it? Are we done? No, we are not finished. So we need to find a general form that we are going to consistently use to find the Laplace transform of any power signal. Now, let's say if n is equal to, let me use a different color. Let's say n is equal to 1. So if n is equal to 1, and this is going to be the Laplace transform of t to the 1, isn't it? Which is the same as the Laplace transform of t, which we found earlier. The Laplace transform of t is that. So this implies that we are going to have n is 1, which is 1 over s, times the Laplace transform. I'm going to use this equation now. The Laplace transform of t to the n minus 1. This is t to the, if n is 1, is 1 minus 1, which is 0. And just gonna carry it over, which implies that we have 1 over s. T to the 0 is 1. So we are going to have the Laplace transform of 1. What is the Laplace transform of 1? We found earlier in our earlier section that the Laplace transform of 1 was 1 over s. The Laplace transform of a constant is 1 over s. If it was 2, it will be 2 over s. If it's 3, it's 3 over s. 4 is 4 over s, etc., etc. So, is the Laplace transform of 1 over s times 1 over s, which is 1 over s squared. So, the Laplace transform of t is 1 over s squared. What if n is equal to 2? Okay, we can do exactly the same because we are trying to find the general formula of t to the n. We are going to have the Laplace transform of t squared, and which is n minus 1. So this is going to be n is 2 over s times the Laplace transform of 2 minus 1, and 2 minus 1 is just t. Okay, so now we just need to find the Laplace transform of t, which we have already found above here. So this is going to be 2 over s times the Laplace transform of t, which we found to be 1 over s squared. Okay, so this is times 1 over s squared, which is going to be 2 over s to the third. Okay, what about if n is equal to 3? Again, if n is equal to 3, this implies that we have the Laplace transform of t to the third, and t to the third, n is 3, so we take 3 over s times the Laplace transform of t to the third. 3 minus 1 is t squared. So this is 3 over s times, remember we found our t squared. T squared is here, and t squared, these are the results, this and that, is 2 over s times 1 over s squared, which is 3 over s times 2 over s times 1 over s squared. This can be written as 3 factorials over s to the fourth. Okay, now we can see a pattern that is coming. We had 1 on top, we have 2 on top, we have 3 on top. Maybe if n is equal to 4, maybe we're gonna have 4 on top, 5, etc. Let's try 4, and we can conclude maybe from there. What if n is equal to 4? This implies that we have the Laplace transform of t to the fourth, which is equal to 4 over s times the Laplace transform of, if it's 4, 4 minus 1 is 3. So the Laplace transform of t to the third, which is equal to, we have 4 over s times the Laplace transform of t to the third, which we found already. So we're just gonna put the results down. I mean, if you want to be very fast, you can just say times the Laplace transform of 3 factorials over s to the fourth. But I want to write everything down so that you can see the pattern. So this is 3 over s times 2 over s times 1 over s squared, which is 4 factorial over s to the fifth. So now, as you can see, this is just patterns, and it's going on, etc., etc. As you increase the power, so does the power at the bottom, so does the factorials, etc., etc. So the general form, we can write it as the Laplace transform of t to the n is equal to n factorial over s to the n plus 1, okay, for s greater than 0. So this is our general format.